In this slide, we would like to compare an element that has a pseudo core to that of a transition metal element, which would not have a completely filled d subshell. So, again, valence electrons are the electrons that are outside of the noble gas configuration, or possibly the pseudo noble gas configuration where the d subshells are full. We have example here of argon and compared to potassium. The potassium has an argon core with the valence electron in the 4s subshell with one electron. The arsenic is a situation where you have the pseudo noble gas core, the argon plus the completely filled 3d subshell. We would say there are 5 valence electrons for arsenic. The example that I want to discuss here for a transition metal is titanium. If we count up the total number of electrons that are the superscripts in this electron configuration, there are 22 electrons. 4 of them are the valence electrons that are outside of the argon core. It turns out that the overlap of the 4s and 3d is an issue when it comes to relative energy, and for all practical purposes, the 4s and 3d orbitals are nearly degenerate in terms of energy. As a result, writing it as 4s2, 3d2 versus 3d2, 4s2 is really fairly debatable. Turns out, though, that there is some utility for writing the electron configuration in the order that you see in the abbreviation or the abbreviated form, such that when transition metals form ions, particularly cations, the loss of electrons generally occurs first by removing electrons from the s, and then removing electrons from any kind of d. So one of the very common positively charged ions of titanium is 4+, losing all of the valence electrons, but there's also a 2+ ion that is possible. And in fact, many of the transition metals form 2+ ions. Shown here are the noble gases for the first 3 shells, helium, neon, and argon. And then we also show 3 elements from the second, third, and fourth periods of the periodic table. You can see that in the abbreviated electron configurations, we have the noble gases helium, and neon, and argon as our abbreviation. Therefore, these are the cores. In the case of oxygen, which has a total of 8 electrons, 6 of those electrons are the valence electrons, and they are the ones that are normally involved in bonding or give us some information about the type of ions that the element will form. And so, for example, for oxygen, we could add up to 2 more electrons to form an ion which would have a 2 negative charge, and that would completely fill that shell, giving us a noble gas configuration much like neon. Turns out oxygen 2- is quite stable. Likewise, for sulfur, which is right underneath oxygen, if we added 2 electrons to the 3p orbitals, we would have an electron configuration of 3p6. This gives an argon electron configuration, which is a closed shell, again, a very stable electron configuration. Finally, if we were to look at selenium, the valence electrons are in the 4s2 and 4p 4 configuration, and of course selenium indeed forms a 2- ion by adding 2 more electrons to completely fill that shell. Alternatively, in some cases we can remove electrons, and that is going to form positively charged ions. So, for example, sulfur often will form situations where we might have 4 plus or possibly even 6 plus by completely removing all of the valence electrons. Likewise, selenium forms a 4 plus ion, or it also forms a 6 plus ion. On this slide, we have the orbital diagram for the phosphorus atom. The orbital diagram will show us the number of paired and unpaired electrons that are possibly useful for forming bonds. So we have the possibility of having, for phosphorus, an electron in each of the 3p orbitals. And so it turns out that one of the very common things to do is to form 3 bonds with other elements. Likewise, if we take a look at the excited state for a phosphorus atom, we can promote an electron to some higher energy level. In this case, we've promoted one of the electrons from the 3p subshell into a low-lying 4s type orbital. That's not the only excited state. In fact, there are an infinite number of possible excited states. But the key here is that this excited state does not follow the Aufbau principle for filling the electrons into the electron configuration, and essentially creates a hole, an energetic hole in the 3p orbital. And of course, this electron in the 4s could fall back down into the ground state and would give off light in the form of electromagnetic radiation. On this slide, we give an example of a situation that does not follow Hund's rules, and therefore this orbital diagram is not the ground state. It happens to be one of the possible excited states where one of the electrons in the 3p subshell for phosphorus is not the same spin as the other two, and we would have to have added some electron or some energy to have that electron configuration result in this orbital diagram. Likewise, if we had 2 electrons in the same orbital with the same spin, this would violate the Pauli exclusion principle, and then would also not be permissible in terms of an orbital diagram for phosphorus. Shown here are some electron configurations that violate the building up principle, the Aufbau principle. The main problem is associated with the nearly degenerate situation for the s orbitals and the corresponding d orbitals for transition metal elements. Quite often, these exceptions to building up principle are a result of either half-filling shells, which is a stable situation, or possibly the situation where we have a completely filled shell that is particularly stable. So, for example, in the case of chromium, by having or promoting an electron from the 4s into the 3d, we have a half-filled S shell, subshell, and a half-filled D subshell. So chromium happens to be very, very stable in that regard, and this accounts for its electrical properties pretty nicely. Likewise, in the case of copper promotes an electron from the 4s into the 3d to completely fill the subshell and have a half-filled 4s subshell. These are exceptions, and we will not focus in too much on all of these exceptions, but you should be aware that there are these exceptions.